Welcome to The Explainer, where we're going to dive in to one of the most maddening problems in software development, the moment your application just freezes. We're going on a hunt for the silent killers in Java multithreading that are really responsible for this.
So let's kick things off with a mystery that I'm pretty sure you've all encountered. Your application just stops. It hasn't crashed, your CPU is basically asleep, but nothing. It's completely unresponsive. So what on earth is going on here? To get to the bottom of this, we've got to understand the three main villains of the concurrency world. So here's our plan. First, we'll introduce the culprits. Then we're going to unmask each one: Deadlock, Livelock, and Starvation. After that, we'll build a playbook to beat them, and then finally, we'll make sure you can ace any test on this stuff. Okay, let's get into it. Our targets are Deadlock, Livelock, and Starvation. You know, these three are the sneaky culprits that can quietly bring even the most robust multi-threaded application to a grinding halt. Just understanding them is really the first big step to writing code that doesn't break under pressure. First up on our most wanted list is the most famous of the bunch, Deadlock. The best way to think about it is like the worst traffic gridlock imaginable for your threads. It's a situation where everyone is stuck waiting for everyone else and absolutely no one can move. So what does that really mean? Well, a deadlock is a permanent standstill. Your threads are still alive, they haven't crashed or anything, but they are blocked forever. And that's why your application is totally frozen, completely unable to make any progress. And this right here shows you the classic trap perfectly. Just look at that cycle. You've got thread A, it grabs lock 1, and then it waits for lock 2. But at the exact same time, thread B has grabbed lock 2 and is now waiting for lock 1. It is a perfect catch-22. Neither one is going to give up its resource, and that creates a circular wait that leaves them stuck. For good. Now, here's what's so interesting about this. A deadlock can only happen if all four of these conditions, what we call the Kaufman conditions, are met at the exact same moment. And you know what? That's the secret to defeating it. You don't have to solve all four of these problems. If you can just break one of these conditions in your code, you stop the deadlock from ever happening in the first place. So, how do we actually break one of those conditions? Well, to prevent that circular wait condition, for instance, you can just enforce a strict lock ordering. That means all threads have to get their locks in the exact same sequence every single time. Or an even simpler fix is just to use timeouts, so a thread will eventually give up waiting after a little while. All right, on to our next villain, Livelock. Now this one is way sneakier than Deadlock. And why is that? Because your application looks busy. Your CPU usage could be totally maxed out, but just like a car spinning its wheels in the mud, it is making zero progress. The key difference, as you can see right here, is the state of the threads. With Deadlock, they're blocked. With Livelock, they're actually active and running. They're constantly trying to do something, failing, and then immediately trying again, all while being too polite to just grab what they need. They get stuck in this endless cycle of failure. This is hands down my favorite way to think about it. It's like two super polite people stuck in a hallway. One person steps aside to let the other pass, but the other person does the exact same thing at the exact same time. So they just keep mirroring each other's moves, endlessly yielding but never, ever getting past each other. They're active, for sure, but they are going nowhere. This table is basically your diagnostic cheat sheet. If your app is frozen solid and your CPU is just sitting there doing nothing, you should immediately think deadlock, your threads are blocked. But if the app is unresponsive and your CPU fan is screaming at 100%, you've probably got a Livelock, with threads stuck in a runnable state, just burning up cycles for nothing. So how do you break out of this frantic dance? Well, you have to introduce a little bit of chaos, a little randomness. So instead of having your threads immediately retry an action, you make them wait for a small, random amount of time. That little bit of unpredictability is usually enough to break the symmetry, so one thread can finally get through and make some progress. And that brings us to our final villain, Starvation. Now this one is probably the most subtle of the three. It's not about threads being stuck or spinning in circles. It's about a thread being consistently and unfairly ignored, just left waiting for resources that it never, ever gets. What this really means is you've got a thread that's ready and able to do its job, but it's just perpetually denied the chance to run. And why? Because other more greedy or maybe higher priority threads keep jumping ahead in the line, hogging all the CPU time, and leaving our poor thread to starve. A classic cause of this is misusing thread priorities. If you set one thread to the absolute highest priority and another to the lowest, the system scheduler might favor that high priority thread so much that the low priority one pretty much never gets a chance to run. It's effectively being starved of any CPU time. Now, the key difference to remember is this. Deadlock is caused by a fatal circular dependency, right? But starvation is fundamentally a problem of unfairness. The good news is that unlike a deadlock, recovery is actually possible. If those greedy threads ever finish their work, the starved thread might finally get a turn. But it's still a huge red flag that your design is flawed. So the way you fight this is by enforcing fairness right in your design. For example, in Java, you can use something called a fair lock. All this does is grant access to threads in the exact order that they asked for it. Strictly first come, first served. It's basically like setting up a proper digital queue that prevents anyone from cutting in line. Okay, so we've unmasked all three of our villains. Now it's time to build our defense. Let's put together a playbook of strategies to keep these problems out of our applications from the very beginning. This right here is your core playbook. And these aren't complicated tricks. They're really just simple disciplines. Things like always acquiring locks in the same order to stop deadlocks, using timeouts so you can escape a potential gridlock, and using the modern Java APIs that just handle so much of this complexity for you. Following these rules can really prevent these issues before they even have a chance to start. And if you remember just one thing from this whole explainer, please make it this quote. Trying to hunt down a deadlock with a debugger is an absolute nightmare. The only real way to defend against it is to design your locking strategy carefully from the very beginning. It is a design problem, not some simple bug you can just patch up later. And finally, let's make sure you can prove you've actually mastered these concepts, whether that's in a tough technical interview or when you're architecting your next big system. Knowing the theory is one thing, but being able to articulate it correctly is what really sets you apart. Okay, please be ready for these common interview traps. A deadlock is not an infinite loop. The threads are blocked, they're not looping. A live lock is not a deadlock. The threads are active and spinning, not blocked. And remember, thread priority is just a polite suggestion to the operating system scheduler, not a guarantee of execution order. Nailing these distinctions really shows you know your stuff. So let's wrap this all up with this one key idea. Deadlock blocks, live lock spins, and starvation denies. All three of them are simply symptoms of a poor concurrency design. They aren't just abstract academic problems. They are real-world failures that you can and should prevent. And by understanding their causes and applying the right strategies, you can build applications that are robust, efficient,